So in today's class, we will look at a few other things. So it's kind of a sort of a random walk that we will do to cover a few things. Okay, so the first thing that we are going to look at is how do you project a vector onto a subspace, right? So how do you project, for example, you have a vector here, let's say V, and I want to project it onto this, let's say a vector on a subspace, one-dimensional subspace U, right? So what do you do? What is the projection? What is the projection? So how do you project? So U is a vector, right? Let's say n cross 1, and V is also another vector n cross 1. So I want to project V onto U. We saw the projection, right? So this is how we do it, right? So let me just write one thing. So you take a vector, okay? So let X be in Rn. Okay, so it's a vector in Rn. Okay, and X perp is orthogonal to X. Okay, so what do you mean by that? You take X transpose X perp, you will get 0. Right? You will take a perpendicular vector, right? So what can you say about this? So suppose I take AI minus, so remember X perp is a column vector, X perp transpose. So what can you say about this matrix? See, this is an n cross n matrix, right? X perp is n cross 1, transpose is 1 cross n, so you get an n cross 1, n cross n matrix, which is rank 1 matrix. I take identity matrix and subtract this rank 1 matrix. So what can you say about this kind of a matrix? And also, what can you say about this matrix? Let's see if there is some use to this, right? What can you say? Let's look at this, right? So suppose I take X. So I'll do one thing. Okay, so I'll take I minus X perp transpose and multiply by X. What do I get? What is X perp transpose X? 0, right? It's inner product of orthogonal vectors. So the second term will be 0. What will be the first term? X itself. That means if you project, so if you look at this matrix, you take this matrix, multiply by X, you get the vector itself, right? That's a nice property to have, right? Let's look at another property. So what is, maybe we'll write it as 1. What is the other property? So suppose I take this and I multiply by X perp, what do you get? Well, let's also add a condition here. Okay, so let's assume that this X perp has unit length of this X perp is unit. I can always do that, right? I can take the perpendicular and normalize it. What can you say about this? What is X perp transpose X perp? It's the norm of X perp square. What is norm of X perp square? Huh? It is 1, right? So now what do you get here? It's X perp minus X perp transpose X perp is 1. You will get X perp itself, which is 0. So what does that mean? You take the matrix, multiply by X perpendicular, you will get 0, right? But if you multiply by X, you get X itself. So what can you, so let's say, let me write these observations, right? So observations. So what is the first observation? Basically, I'll call this matrix as P, okay? So I'll call this matrix as P. Okay, so what is this P matrix doing? P times X perp is X perp itself, right? Is that correct? No, it's X perp is 0, right? Okay, just a small, sorry for the confusion. So let me use this as X, okay, Px. Okay, let me call this as Px. So Px, X perp is 0. Px, X is X itself, right? Looking at this, what can you say? You can think of this Px as projection, right? If the vector itself is already in the span of x, and you say I want to take that vector and project it onto the subspace, it's like this. I take a vector and I ask you to project it onto this plane. What do you get? You get some projection. But if the vector is already in the plane, what do you get? If I say project it onto this plane, you get the same vector, right? If I ask this vector, if I give you this vector on this two-dimensional plane and ask you to project it onto something orthogonal, what do you get? 0, right? So this mimics a projection. By the way, this projects onto a vector space spanned by a vector x. Suppose I want to span, let's say, a two-dimensional vector space. Suppose you have x1 and this is x2. I want to project it onto the subspace spanned by this x1, x2. What is the span of x1, x2? All possible, right? So how do you do this? What is it that you will do? How do you construct a projection? So one thing is, I can project it onto x2, right? So what do? I normalize x2 to get x2 dash. I can project it onto x2 easily. I know how to do that. If I want to project it onto x1, I want it to be a unit vector. One thing that I can do is, since it spans the entire space, I can just take, let's say, x1 dash. X1 dash, x2 dash are orthogonal to each other. It spans the entire, it spans the vector space spanned by x1, x2, and they have unit norm, right? I can do the following, right? So I can do x1 dash transpose minus x2 dash transpose, right? Let me call this as p x1 x2, okay? Because so I want you to think about what this gives us. Okay, by the way, I want to look at the perpendicular of this, right? So what I will do is I'll take okay, so let me not call this as let me call this as some q, okay, q x1 x2. Check what check the properties of this okay. That is the first thing. The second thing that you are going to do is I want to project it onto span of x1 x2. So construct such a matrix, okay? So construct p x1 x2 projection matrix onto span of x1 x2, okay? So in general, if you have a matrix, for example, let me call this as PV. If PV is supposed to be a projection matrix, right? So if PV is a projection matrix onto a subspace V, which is suppose that's a subset of Rn, then what are the properties that we need? PVV should be equal to V for all V in V, right? If you take a vector V in V and ask you to project onto V itself, you should get the same vector, right? You take a vector on the plane and ask you to project onto the plane, then you should get the same vector, right? So PV of V perp, okay, so it should be equal to 0 for all V perp belonging to V orthogonal. So this symbol means it is all those vectors orthogonal to the vectors in V. Okay, it's called orthogonal subspace, right? I had defined this earlier. Okay, this is a general property. In fact, you can explicitly construct matrices which has this property for a given subspace. Okay, the reason why I want this, I wanted to talk about this is because there is another way of projection, right? So I had given a mathematical or a optimization characterization of projection, right? I want that vector in the subspace which is close to the vector V, right? That is called projection, right? So for example, if I want to do this projection of Okay, so if I want to project U onto V, onto a vector space V, all that I have to do is I have to ensure that